LeetCode problem 23. Merge case sorted lists. Isn't just a warm-up on linked lists. It mirrors real-world systems that constantly merge sorted streams. Think log processes, distributed queries, or streaming data pipelines. Brute force works, but it crashes at scale. So how do we merge smart, not slow? Let's dive in and sort like a duck slicing through current. All right, ducklings, we're starting with brute force. No optimization yet. We'll scoop up every value, sort the pile, and rebuild a new list from scratch. Let's see how that looks in code. First, we drop all node values into a dynamic list. It gives us a clean, flexible space to collect everything before sorting. We scan each linked list in the input. For every non-null list, we traverse its nodes and toss each value into our collection. That flattens all data into one line. With all values collected, we sort them. That guarantees our final merged list will be in ascending order, just like the inputs. Time to build the new list. We use a dummy node to anchor it and a pointer to help us attach new nodes as we go. For every sorted value, we create a node, link it, and advance the pointer. That's how we rebuild the full list in order. Once done, we return the node after our dummy, the real head of our freshly merged list. This runs in big O of n log n being total nodes. With 10,000 elements, just the sort is over 100,000 operations. Space is also big O of n since we store all values. Simple? Yes. Scalable? Not really. Watch out for memory spikes on big inputs. So how do we skip all that sorting? What if we merge one list at a time, like ducks crossing a stream, one after another? This step-by-step method keeps things ordered and avoids the value pile-up. Let's handle edge cases first. If the input is null or empty, there's nothing to merge. We just return null and move on. If we do have input, we set our initial result to the first list. That's our starting point. We'll merge the rest into it. We loop through the remaining lists, merging each one into our running result. Always two at a time, nice and steady. Once they're all merged in, we return the final result. That's our fully combined list. To merge two lists, we call a helper. We start by creating a dummy node. It keeps the code clean and avoids head-edge cases. We use a pointer called current to track where to attach new nodes in our result as we compare values. In the loop, we compare values from both lists. Whichever's smaller gets added, and we move that list's pointer forward. Each time we attach a node, we move current forward too. That way, we're always pointing at the last node in our result. Once one list is empty, we attach the rest of the other list directly. Since both were sorted, we're still in order. We return the node after the dummy, the real head of our newly merged list. Time-wise, this takes big O of k times n, k lists, n total nodes. For 100 lists and 10,000 elements, that's 1,000,000 operations. Space is big O of 1, very efficient. But when k grows, repeated merging slows us down. That's because we keep merging into the same result list, stacking work on work. Let's fix that by balancing merges using divide and conquer. We begin with a check. If the input is null or empty, we return null. No merge needed. If input's valid, we call our helper to merge the full range of lists. This kicks off the divide and conquer process. Inside the helper, our base case is one list. If left equals right, we return that list directly. Otherwise, we calculate a midpoint and split the range in half. That's how we build our recursive tree. Next, we recursively merge the left side, narrowing the problem bit by bit. Then we do the same for the right. Splitting both sides keeps our recursion balanced. With both halves merged, we combine them using our toList merge function, just like before. We start the merge with a dummy node to simplify pointer work. No special cases for the head. As we walk through both inputs, we always link the smaller current node. That keeps our list sorted as we go. Once one input runs dry, we attach the rest of the other. Since it's already sorted, we're done without more comparisons. We return the merged result starting after the dummy, completing one full merge step in our recursion. This runs in big O of n log k and space of log k. For 10,000 nodes across 100 lists, that's around 66,000 operations. Far faster than before. It's scalable, interview approved, and production ready. By reducing total merge passes, we save big on time and memory. We started with brute force, simple but wasteful. Then came iterative merging, smarter but slow when k grows. Divide and conquer changed the game. By halving our merge work, we dropped to big O of n log k. It's the real-world solution for high-volume sorted merges. Whether you're prepping for interviews or building robust systems, this trick is a must. Give it a shot and keep optimizing, one clean merge at a time.